In this video, we're going to do some numerical examples to see how we can determine some equilibrium constant values given some concentrations at equilibrium. So here we have a system, and in this system, we're told that we measured some concentrations, and those concentrations are equilibrium concentrations. So at equilibrium, this, and this are the concentrations of the different substances in our system. So if we want to calculate K, we first need to make an expression for K. So K is equal to the concentration of the product to the power of its coefficient, so squared, over the concentration of the reactants multiplied by each other. And we need to make sure that they're put to the power of their coefficients. I don't really need to write the 1 there. I was just showing that there is a 1 here, and there's a 3. So now what I can simply do is plug these values in, and I get my K constant, my equilibrium constant. So I can do 0.20 squared over 0.30 times H2 is 0.10 and it's cubed. And I can punch that into a calculator. So I get 0.2 squared divided by 0.3 divided by 0.1 cubed, and I get 133.33333. But I need to round this to about 2 sig figs, so approximately 130 would be the KEQ. And so since this is larger than 1, this would mean that the products are favored at equilibrium. So that was a simple question where you had the equilibrium concentrations, and you simply had to find a K value by plugging in those equilibrium concentrations into your equilibrium expression. We're going to try a different type of problem now, which is a little bit different but very similar. We have another constant here, or another system here at equilibrium. And we're told that these are the equilibrium concentrations for most of substances in there, but we're missing the equilibrium concentration of water. We want to figure that out. Notice that we have the K value this time, and we have 3 of the concentrations that we need. So we can make a K expression. Carbon monoxide times hydrogen cubed over CH4 times our water vapor. And essentially, this is what we're looking for here. We're looking for that concentration of the water vapor. So I could rearrange this to get the concentration of water vapor. So concentration of water is going to be equal to the concentration of carbon monoxide times H2 cubed over the concentration of CH4 times K. And so that's going to be, let's see, CO is 0.300, H2 is 0.800, and that's cubed. CH4 is 0.400, 0.400, and then the K value was 5.67. Now, just one more thing to mention before we continue with this. You'll notice that I didn't use any units for the K, and that's because even though you can technically have units for an equilibrium constant, it just varies so much through the different exponents that you'll have that we just don't report them. So there's no need to report units for K values. However, there will be a need to report a unit for the concentration that we're looking for here. And that's pretty easy. It just matches the units for the other concentrations there. These are all in molar, so these should be in moles per liter at the end, which is the same thing as molar, the big M. So let's go ahead and plug these numbers in to see what we get. We have 0.3 times 0.8 cubed divided by 0.4 divided by 5.67. And we get approximately 0.067724867 molar, or to the correct number of sig figs, which is, in this case, 3 sig figs, 0.0677 molar. And so this would be the concentration of H2O at equilibrium. If you want to verify your work, you could just take all the equilibrium values that you have there and see if they come up to 5.67 again. So, for example, to check, you don't have to do this all the time, but it's a great way to check. You could do K is equal to, so CO is 0.300, H2 is 0.800 cubed over CH4, which was 0.400, times H2O, which was the value we found. That might be a little bit off because we rounded, but it's no big deal. 0.0677. So let's put that in our calculator and see what we get. When I do that, I get 5.67 again. So that means I did the right job. I put all the numbers where they should be, and I got the correct value for my concentration of H2O at equilibrium. So in this video, we did some numerical examples with the equilibrium expression and finding the equilibrium constant. And then we also saw an example of how we could use the equilibrium concentrations that are given to us along with the equilibrium constant to find an unknown equilibrium concentration. In the next lessons, we're going to take a look at some more complex problems involving the equilibrium constant.